Welcome to this video about the finite element method of the wave equation. Before we start deriving the finite element method for this equation itself, we are going to state the problem definition, so the strong formulation of the equation. Given we have a speed of sound, we have some initial conditions and some derivatives of the initial conditions. We have a boundary condition, Dirichlet boundary condition, and also a Neumann boundary condition, and we have a domain omega and a certain time frame between 0 and capital T. We would like to find the acoustic pressure such that on this given set the partial differential equation itself is satisfied here with some forcing and in the product of the domain and the time. To solve these equations we need some boundary conditions. First of all, on the Dirichlet boundary condition, on the Dirichlet boundary we have the certain boundary condition that the acoustic pressure is prescribed here. We already know what's the Dirichlet boundary condition, and on the Neumann boundary condition the gradient in the normal direction is prescribed by velocity. Additionally, to make the system solvable we need some initial conditions. The initial conditions are also two pairs. First of all, at time 0 we have to prescribe the acoustic pressure inside the domain, and also we need to prescribe the time derivative at the initial step, so that we already know how steep the acoustic pressure is driven. This whole set of equation gives us the strong form of the wave equation, which is now used to derive the weak form and the finite element